All right, today I want to show you guys, following up on doing electron configurations where you've done complete configurations, I want to show you guys how to do noble gas notation, which are shorthand version of configurations. A lot of times people ask me, why didn't you teach us this in the beginning? But you really need to know how to do a complete configuration before you do a noble gas notation. Also, we've used this diagonal rule to do configurations, which is what you get in AP Chemistry, or in college classes. This is what they use. So you can always use that to do configurations, but I want to show you how you can do this from the periodic table as well. So here's the thing, and this is the order of the periodic table is going to go in line with this. So if you're doing a configuration from the table and from the diagonal rule, you're going to get the same answer because you just have to understand how the table is arranged. First of all, as you go across any particular row, that's the level that the outer electrons are in. So all these elements have electrons in level 1, level 2, 3, 4, 5, 6, 7. Notice we only have 7 levels. That's how many we have there for the periodic table. And again, this is just a blank table. It's the same as your normal periodic table. This would represent hydrogen. That would represent helium, lithium, and so forth. And you read it basically like a book as you're going across doing configurations. So, you might say, what do I mean by that? So here's the thing. Think about this. The elements, every particular level has an s orbital. But how many s orbitals are in a level? Just one. How many electrons can you put in those s orbitals? 2 total. Every one of these elements right here end in s. We call it the s block because that's what they end in. And so hydrogen's electron configuration is 1s1. It's in level 1. It's in the first column of the s section. So all of these end in s1 and all of those end in s2. There is no s3 because there's only one s orbital and you only put 2 electrons in it. And so again, so the electron configuration of hydrogen is 1s1. Helium is the only element actually that's out of place on this table. It actually ends in s2, but it's over here in what we call the p block because it can only have 2 electrons in level 1 and then it's full and it acts like a noble gas. The rest of these actually have 8 in their outer level and that makes them full. So it's acting like the rest of the noble gases, which have a total of 8 valence electrons. Alright, so you go 1s2 is the first 2 electrons. Lithium's got atomic number of 3. It's got 3 electrons. You ask where they are. 1s2, 2s1. The next element, beryllium, it's got 4 total electrons. What is its configuration? 1s2, 2s2. What comes next? Go up here. What comes after 2s2? 2p6. That means this section here is the p section. They all have electrons. Their outer electrons are in the p block. They're in p orbitals. And so think about this. There's always 3 p orbitals. How many electrons can you place in them? A total of 6. All of this except for helium. We say, again, this is the p block. That's where all their electrons are in p orbitals. And notice how many columns there are. There are 6 of them. All of those end in P1, P2, P3, P4, P5, and all of these here, the noble gases, end in P6. They end in S2, P6, which is a total of 8 electrons, which is why they're stable. So, what about the next one? So what comes next after? So we go 1s2, 2s2, 2p6, 3s2. And then what comes next? 3p6. Remember, if we say this particular element here, where are its outer electrons? We'd say, okay, 3s2, 3p1. Its outer electrons in 3 because it's in the 3rd column. And so the last one here, again, obviously ends in p6. What comes next after 3p6? 4s2. So we got 3s2, 3p6, 4s2. But this word does get a little confusing. This is the d block. Think about this. They all end in D. How many d orbitals are there? There's a total of 5. You can put 2 electrons in each orbital, so there better be 10 columns here. And there are D1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over there at the end where zinc is. And so again, 4s2, 3d10. So I want to show you real quick. We'd go, okay, here's potassium. How can I use the electron or the periodic table to determine its electron configuration? Here's how you could do it. It's the same thing as what you get up here. You go 1s2 would be where its first electrons are at. 1s2. And then you go down to the next column, 2s2. So 2s2. And then what comes next? 2p6. And then what's next? 3s2. Go across here. The next 6 electrons are in 3p6. And then here's where potassium is, right here. And so it ends in 4s1. It's 4 down, it's 1 across in the S section. If we were talking about calcium, it would obviously end in 4s2. And so there's the electron configuration for potassium. So let's complete this, and I'm going to go back and show you how to make a noble gas notation out of that. 4s2, 3d10. So here's the thing, and this is where it's confusing. Notice, so you fill up 4s2 and then you call that 3d10, but you might go, wait a second, it's in level 4. When you give the D sublevel a name, it's the principal quantum number minus 1. What does that mean? It's the level you're on. Remember, principal quantum number is the level you're on minus 1. So if you're in level 4 and you're starting to fill up these orbitals, we'd say 4 minus 1 is 3. That's 3D because it's actually part of the third level. It's just you fill up 4s before 3D. You don't need to know why. It is what it is. And so again, so we call that 3d1, 3d2, and again, that would be 3d10. It does not apply over here to the p orbitals though. So you fill up 4s2, 3d10, and then that would be 4p1 all the way to 4p6. And then 5s2, and again, this would be called 4d10, and then 5p6. 6s2 gets a little crazy again because this is where the F fill in right here. This is the F block. So it is the F block. They're filling up F orbitals. And think about this, there are always 7 F orbitals. There better be 14 columns there, and there are. And so you go 6s, and this is going to tell you this up here as well. 6s, what comes next? 4f. So this is when you name the F blocks, the principal quantum number you're on minus 2. So this is filling in level 6, so we call that 4f. And this one here is filling in at 7, so we call that 5f. So 6s2, 4f14. And again, it's going along with this. If you follow along up there, and then 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. It's all the same as up there. We're not going to ask you to do configurations for the elements down at the bottom, so don't panic when they get all confusing like that. I'm just telling you, the periodic table is set up based off of where all the electrons are. Now, the other thing I'm showing you today is how to simplify this. So it's called the noble gas notation. What you do is find the element. So here's potassium on the periodic table. We did the whole configuration for it there. Go back to the last noble gas before potassium, which would be this one here, and that is argon. I'll fill it in for you. If you have a periodic table handy, that'd be helpful. And so go back to the last noble gas and just write the noble gas before the element in brackets. Why are we doing that? What we're saying is all of the core electrons for that element are exactly the same as the configuration for argon. So that is argon's noble gas notation. All we need to include in a noble gas notation are the valence electrons, or the outer shell, and those are just the electrons after the last noble gas. They're the ones that are involved in reactions. So you find the element, go back to the last noble gas, put it in brackets, and then just write down the valence electrons that it has after that noble gas. 4s1. So again, that's telling us that potassium has 1 valence electron there. If again we try to do, let's just pick one more before we move on here, so I can show you. This one will be a little more confusing. So we'll take this element here, and let me look that up. What it is? It's molybdenum, and we've got, okay, what is its noble gas notation? So we've got to go back to the last noble gas, which would be this one here, which is krypton, Kr. So we would write Kr and everything after Kr, because those were technically could be valence electrons for that particular element. So the first 2 electrons after Kr are in 5s2, so 5s2. And don't forget, it's 4 over in the D section. We don't call it 5D, it'd be 4D4. And again, that's just the faster way to do notation. Just go back to the last noble gas. And the reason we don't write all of those out, well, they're the same configuration. If we write all those electrons, it would be the same thing as krypton. And those are core electrons. They're not involved in chemical reactions, so we don't need to write them. All right, real quickly, let's do some practice here. All right, for calcium. And so calcium again, so let me move this around here a little bit so you can see that part of the table. and we'll do configuration there for calcium. And all you have to do, again, go back. Here's calcium on the periodic table. There's calcium. I put an X there. I just probably should have put the symbol. So it's calcium. So again, it's noble gas notation. Go back to the last noble gas. It would be argon. Its core electrons would have the exact same configuration as argon, and then write down the 2 electrons that come after that. There you go. It's that simple. So 4s2. As an ion, if it's +2, it actually loses those 2, because remember, ions are more stable because they're actually losing or gaining electrons that have a noble gas notation. It would now be the same thing as argon, because again, it just lost those 2 to become +2. Do sodium on your own. The answers are at the end of the notes. Then let's look at sulfur there real quick. Let me find sulfur on the periodic table. It is right here on the table. So again, that's sulfur. And we want to do a noble gas notation for sulfur. Go back to the last noble gas, which is this one here, which is neon. And you'd put Ne in brackets. And everything after neon would be the valence electrons for sulfur. So the first 2 would be in 3s2, 3p, 1, 2, 3, 4 across in that section. So 3s2, 3p4. Noble gas notation. If it's -2, that means it actually has 2 extra electrons, which is why it's very stable as an ion. So it'd be 3s2, 3p6. Do nitrogen on your own. Again, you can check those answers in the notes. Iron, there's iron right here. So let's go back to the last noble gas, which is argon. So go back to argon and then write down everything after the noble gas. Those are potentially valence electrons. 4s2, 3d, it's 6 across in the d section. Remember, it's the level you're on -1 when you're talking about those. And then the last thing I want to show you here is argon. You know, what if it is a noble gas? Do you just write AR? Technically, you should write in a noble gas notation all the potential valence electrons an element has. So you need to go back to the last noble gas, which is neon. That's Ne, by the way. And neon. So go back to neon and write everything after that. 3s2, 3p6. 3s2, 3p6. Let me know if you have any questions. Good luck. Again, your practice, you had one after each problem to practice yourself to make sure you know how to do that.